very honored to come. So I'm going to talk about the geometry of CY modular. That means the geometry of the modular space of polarized Calabi-Yau manifold. I will explain why we need polarization of what the Calabi-Yau manifold is, what the polarization means, why we need polarization. And by geometry, we mean differential geometry. And we try to understand the modular space of this very important manifold, Calabi-Yau manifold, understand its modular space through the differential geometric method, through geometric analysis. So before I give my talk, let me first give an example, which is more or less elementary, but also it's interesting in string theory. So we start with a Kähler manifold X, and we assume that such a Kähler manifold has an open neighborhood cover, and we assume that on each neighborhood, on each coordinate neighborhood, there exists a holomorphic function U of U alpha, such that the Kähler metric, such that on this coordinate neighborhood, there's a holomorphic coordinate system Z1 through Zn, and under such Z1 through Zn, the Kähler metric can be written in this way. So this is not the complex Hessian because U is holomorphic. So this is the holomorphic Hessian, but we take the image part of this function and assume that the Kähler metric can be written like this under this very special neighborhood. So if this is true, then of course such a Kähler manifold is very special. So in the sense of Strominger, string theorists, and Dan Fried, we call this a special Kähler manifold. So in general, of course, we cannot reach that. Even locally, it's not possible for a Kähler metric to be written in such a way. So why are we interested in special Kähler manifold? Well, we can compute its curvature. So when we compute its curvature, so my convention of the curvature tensor is this. So in Kähler manifold, plus this first order term. So in this sense, when we say negative, we really mean its curvature should be positive. So the Ricci curvature is negative of the trace of kk of that. This is my convention. But if we look at this, we will see that this is a locally holomorphic function, the image part of the locally holomorphic function. So actually, when you take second derivative, it goes away. So what remains will be the first order term. But the first order term is a quadratic term. It's a convex quadratic term. So, well, after all, we can compute the curvature tensor is this. So here Uijk is just, as you expected, the third derivative of the holomorphic function. And so with that, we can write down the scalar curvature of the metric, which is the trace of everything. So the scalar curvature is apparently a positive function, at least a non-negative function. Okay, so this was done before by string theorists. So what is interesting is, well, we can observe with this convexity, basically it's the multiplication of 2d something multiplied by d bar. So it has convexity, so you can see that the Ricci curvature of this manifold has to be non-negative. And the scalar curvature is positive. And moreover, if the scalar curvature is identically 0, that means this Uijk has to be 0. That means the curvature tensor has to be 0. So if we do one more times, if we take derivative for another, if we take another set derivative twice, then we can actually get a Bochner type formula. So by taking the by taking the Laplacian on this, we can get something. Because if you take Laplace on this Lu, then these two are holomorphic and anti-holomorphic. So when you take derivative, so the holomorphic part is acting on this, the anti-holomorphic part is acting on the other side, which produce something positive, and we can throw away. So what is interesting is when derivatives are acting on this G upper ij, G upper mn, G upper kl, we will get curvature. And through some computation, we can prove that, so actually I explained that. So the Bochner formula is, so this is the fourth order derivative. And when the Laplacian is acting on G upper ij, we will get curvature, but curvature is in terms of the third derivative of uijk. So we will get something like this. And by Schwarz lemma, by Cauchy inequality, we will get something that like delta lu is greater than a positive number times lu square. So why this is interesting? Because we have the generalized maximum principle. So this is true on Riemannian manifold. On any Riemannian manifold such that the Ricci curvature has a lower bound, and if there is a non-negative function f such that delta f is greater than f squared, then f has to be 0. So this is trivial if x were compact, because we can use maximum principle, and at the maximum point, the gradient is less than or equal to 0. But it's also true if, with this curvature assumption, and with assuming that f is non-negative, and assuming that gradient f is f a little bit, with f with the power a little bit greater than 1, then we can pretend that the maximum point of f exists and is reached. So we can use maximum principle. So this is called the generalized maximum principle. Okay, so for using the generalized maximum principle, we can prove the following result. So if x is a complete special Kähler manifold, then x has to be flat, has to be totally, the curvatures are identically 0. The reason is we already have the gradient rule is bigger than lu square up to a constant. And the lu is non-negative, and the Ricci curvature of x has a lower bound. So putting these three together, we will get lu is identically 0, and which implies the sectional curvatures are 0. So this tells us that sometimes we don't, this special Kähler manifold came from string theory, but it is that the special structure of the Kähler metric, the special expression of the Kähler metric that makes the very strong restriction on the global structure of the manifold. So basically is that the Kähler metric is, the Kähler matrix is this. We do not have to know what the specific holomorphic function u, but we can still get the curvature estimate. So this is our example, and why we are interested in such an example, because Calabi-Yau modular space, if you study its Weil-Petersen geometry, study the Weil-Petersen metric, it is, of course, more complicated than the above-mentioned example, but it's similar. Okay? It has the similar structure. Basically, we do not have to know what specific Calabi-Yau modular space, what specific modular space of a specific Calabi-Yau, we can tell some result. Okay. All right. So we are going to talk about the following things. So we consider a polarized Calabi-Yau manifold, XL, where X is a Calabi-Yau manifold, and which by definition, it is a simply connected compact Kähler manifold such that the first term class is 0, or in other words, its canonical bundle is trivial. And for the sake of simplicity, we will always assume that the manifold is simply connected, and a little bit more is that we assume that the Calabi-Yau manifold we are interested in is called the primitive. So by primitive, we mean that suppose X is a Calabi-Yau n-fold. So for such a manifold, the most interesting cohomology group is HNXC. Okay. So we assume Calabi-Yau manifold is primitive. We assume that X is primitive So if H of k or other lower cohomology group when k is greater than 0 and less than n, well, maybe greater than 2. Sorry. Sorry. I mean the font. HK0 to be 0 for 0k less than n. Okay. We just assume any uninteresting cohomology groups are our 0. And we assume that L is an ample line bundle. That means we have a line bundle such that it admits a metric with positive curvature. So the natural question is why we are interested in, why we need the polarization instead of studying a Calabi-Yau manifold, why we need to assume it's polarized. So from algebraic geometry point of view, this is quite obvious. And so from differential geometry point of view, it is because the following result of classical result of Yau. So in almost 30 years ago, Yau proved the following. So for a compact Calabi-Yau manifold, given any cohomology class of the Kähler metric, there exists a unique Kähler metric which is Ricci flat. So the uniqueness is up to a fixed cohomology class, omega. So, or in other words, if you don't fix a cohomology class, there are infinitely different cohomology Ricci flat metric. So in order to relate the manifold, which basically its complex structure, to differential geometry, we want uniqueness. We want that fixed complex structure, there's some unique best possible metric. So for that reason, we need to fix a cohomology class, or more or less equivalently, we need to fix a polarization, fix a line bundle over it. So this is what I said. And why we primarily interested in Calabi-Yau manifold, why we are interested in its modular space. The reason is Calabi-Yau manifold is such a nonlinear object, and we wish to linearize it. And so modular space provide the platform for us to compare those Calabi-Yau manifolds that are close to each other. So it gives us a platform to take derivatives, basically. So what I mean is, instead of studying one Calabi-Yau manifold, we put all the similar Calabi-Yau manifolds together, and we compare them. So this is the jungle of Calabi-Yau manifold, and this is the modular space. And before we are able to study the Calabi-Yau manifold, we need to study the modular space. And so again, I'm only interested in the differential geometry aspect of Calabi-Yau manifold. So from differential geometry point of view, the way to study the modular space, or the way to study any manifold, would be we start from local properties. Basically, we compute curvatures and very local things. And then we use the local information to obtain global information. But for Calabi-Yau, we have something more. So first, of course, like in most cases, we study local properties of modular space. And then we are also interested in the semi-local or semi-global properties. Those are we want to study the modular space, which is the neighborhood at infinity. So local properties basically is a neighborhood of any given point of the modular space. And this is completely a linear problem. And the semi-local means when the central point is infinity, and we have some kinds of singular Calabi-Yau, and we want to study the very local nature of the modular space. And the third thing is we want to study, of course, the global property of the modular space, which is more or less very little is known. Okay, so I know there are a lot of experts in deformation theory, but I still want to give a very, very quick review of Cordella-Spencer's deformation theory of complex structures. So we start with a Calabi-Yau manifold, and we want to linearize it. So the way to do it is as follows. So we assume that Z is a compact complex manifold, and a complex structure J is a real operator from the complexified cotangent bundle to itself is a bundle homomorphism, but is a real operator. It satisfies J squared equals 1, and of course plus some integrability conditions. So for fixed frames, we can write J in terms as square root -1i, negative square root 1, negative i. Basically, by writing this, we split the complexified tangent bundle in terms of the holomorphic 1-0 bundle and the anti-holomorphic 0-1 bundle. So a variation of the complex structure, or rather in this formula, is a variation of the almost complex structure, is a real matrix such that when epsilon is very small, we wish that J plus epsilon A square equals -1 plus O epsilon square. So this is defined to be a deformation. Okay, so if we take this and we take the first order derivative, then we will have the following equation that AJ plus JA is equal to 1. And since J is of this specific form, we can quickly find that A must be of this form, where the constant 2 is just for later convenience. So that means this A, or the variation of complex structure, is completely determined by the following bundle map, A1 from T10Z, the holomorphic tangent bundle, to T01Z. So, or in other words, we can write A as, if you dualize this, then this A is complete, can be represented by, can be identified with a T10, the holomorphic tangent bundle valued 0-1 form. So we haven't touched the integrability condition yet, but so this is basically for the deformation of the almost complex structure. So that is governed by such a quantity. Okay, so when Z happens to be a compact Riemann surface, we can use the conformal Kähler metric to identify this to the so-called Beltrami differential. And the Cordella-Spencer map is basically given by just in the epsilon direction deformation can be identified with a form like this. So next we come to the integrability condition. So it's not hard to see that with this deformation, then we can write the new complex structure. Sorry. We can write the new complex structure in terms of the d-bar operator. So the new d-bar operator, d-bar phi, is equal to d-bar minus phi. And by the Nielenberg-Newlander integrability condition, such a deformation, if it has to be a complex structure, must have such a identity. So d-bar square, basically d-bar square has to be 0. So if we expand this, we will get a partial differential equation of phi. So in terms of using the notation of super Lie bracket, we can write things like that. It's basically, if we square this, we will get 3 terms, but one term is d bar square, which is 0 by definition. The other term is d bar phi, and the third term is essentially minus phi wedge phi. So well, it's not really a wedge because phi is a operator, is a tx valued one form, but so phi acting on this phi. Okay, but we can have some. So this. So we're using the super Lie bracket notation. Then this phi wedge phi can be written as half half of phi Lie bracket phi equals 0. So this is the partial differential equation we need to solve in order to find the deformation. This is the integrability condition. So I haven't given the details. So the idea is if X is a given Calabi-Yau manifold or a given compact complex manifold, so if I have a phi, let's say phi 0 belongs to H1 XTX. Well, actually, I need to say more about this. So this is the infinitesimal deformation, which we can view it very quickly in terms of the following picture. So if we have a family of compact complex manifold, so the most natural way to compare two neighborhood, two close complex manifold is through the so-called harmonic map. So if we have X here and the xt is very, very close to X, so then if they are all Kähler manifold, then naturally the harmonic map exists. And so when t goes to 0, this harmonic map shrink or linearize to something called harmonic form. Okay, so in this sense, when this goes to 0 and you linearize it, you can basically say this is the infinitesimal deformation of the complex structure. And such a complex structure, by this point of view, can be viewed as an element in the cohomology group, or by the Hodge theory, we know that this is the infinitesimal deformation, which originally was harmonic map. When you shrink it, it becomes a harmonic Tx valued 0, 1 form.